So class, today I'll be doing an example of what I'd like to call a compound pulley problem. A compound pulley is exactly what it sounds like. It's going to be a pulley that's got two different radii on the same pulley. And I'm going to just make up a problem to solve. So I have an inclined plane that is fixed to the table. Let's call that incline angle theta. And let's suppose it's a rough incline, mu sub k. And it's got a compound pulley. This I have to draw a bit carefully. So it's got a big radius, capital R, and a small radius, little r. And these two pulleys are joined together, either glued together or they're made from the same material. The details of how these pulleys are constructed does not really matter here, although you can go to town calculating the moment of inertia of something like this. If I give you the density and the thickness of each pulley and the radius of each pulley, that's a problem in itself, but I won't be doing that here. So I have some thread wound around the smaller pulley that controls the descent of this mass. Let me call the mass of this object m, and let's suppose initially that it's moving down like this. Now there's also thread wound around the outer parts of the pulley, and that's controlled by this descending cylinder. And just for the sake of making this problem interesting, let's assume the cylinder is really massive. It's made of something like uranium, and that is something like a small block of wood. So definitely uranium is going to pull the whole thing down, but somehow maybe I've helped this a little bit. So initially it's moving down. So the problem is for us to find the time taken to stop, which I'll call Ts, and the stopping distance. Which I'll call L sub s. So how long does it take for this block to stop, and how much distance does it cover? But basically what I'm asking you to do is to find the acceleration of this block, and so we have to solve the whole problem to do that. You cannot do this without doing that, and you cannot do that without doing this, so everything is connected in this case. Let's draw a free body diagram, and I'll be a little bit reckless and draw the free body diagram on the objects themselves. So T2, and that's going to be a pretty big arrow for mg, because remember the acceleration is going to be down. Now because the pulley is different radii, they're going to move differently. So I'll call the acceleration of this larger mass, capital M, I'll call the acceleration of that A2. The acceleration of this is going to be smaller, and I'll call that A1. The pulley is going to have an angular acceleration, which I'll denote by the curved double shafted arrow, alpha. So before we go any further, let's actually analyze, before I even go and write the forces on the other objects, let's analyze what the constraints are. What keeps this system moving without any slipping? So the constraints are the following. If I let this pulley move by an angle theta, the little pulley and the big pulley move by the same angle theta. So theta is certainly equal to the arc distance traveled by the little pulley divided by the little pulley's radius, and it's equal to the arc distance traveled by the big pulley divided by the big pulley's radius. If I differentiate this, I'm going to get the next equation, which is omega equals the tangential speed and this is the tangential speed of the outer pulley divided by the outer distance. And when I differentiate once more, I get alpha equals A1 over R, and that's also equal to A2 over capital R. So that's the relationship between A1 and A2. So let me save that for later. A1 equals R alpha, and A2 equals capital R times alpha. As you can clearly see, A2 is bigger than A1 because little r is less than capital R. Now, once you have the constraints all worked out, the rest of the problem is just Newton's second law. So let's examine the free body diagrams of the remaining two objects. T2 will act also by Newton's third law like this. And then remember, the whole thing is accelerating like this, so clockwise. So we need T1 to be a little bit less than T2 to make that happen. So T1 I'll write like that, and this is T1 over here. It's going down, so there's also a force of friction acting here, force of friction kinetic. And here I'm going to be extremely informal. I know you've drawn your free body diagrams with much greater care than I'm going to do now. This is the normal force, Fn, and mg is going to act down like this. So we can split it up right away into components. So in the downward direction, you're going to get, this angle is also theta. So this is going to be mg cosine theta, because that's the adjacent side to the angle theta, and this is going to be mg sine theta. So I believe, drawn everything I need to draw, so let me just give you the choice of axes here. In keeping with my custom, the direction of acceleration is always positive, and here my choice of axes would be, for the same reason, down. So now it remains to write Newton's second law for each of these things. Let's start with a pulley. Newton's second law for the pulley is the sum of all the torques about the center of mass is equal to the moment of inertia of the pulley times alpha. Now the moment of inertia of the pulley, as I mentioned earlier, you can calculate it in a very complicated fashion. If you know the density of the pulley, the different radii, and the thickness of each pulley, you can calculate it. I won't bother doing that. I'll just call it I sub p. Now remember, all the torques that promote clockwise direction is positive. Clockwise rotation is positive. So capital R times T2 times the angle between capital R and T2, which is going to be 90 degrees, sine 90, and then little r is not promoting clockwise. Little T1 acting at little r is not promoting clockwise, so that gets a negative sign. So that's little r times T1 sine 90 is equal to I sub p times alpha. Let me just simplify that a little bit. That's RT2 minus RT1 equals IP alpha. This cannot be made to look any nicer, so I'll just call that equation 1 and move on to the next step. Let's look at the mass on the incline next. The incline mass, you have, first of all, in the y direction, the block's not flying, so sum of all the forces in the y direction is 0. Well, that tells me that the normal force is just equal to the component of gravity in the y direction, which is mg cosine theta. Now what about the x direction? Sum of all the forces in the x direction is mass times the acceleration in the x direction. That's what Newton said. So in the x direction, remember that's positive x, so that's going to be T1 plus force of friction kinetic minus mg sine theta. M times A1, because that's the acceleration of the block. we can use the law of friction. The law of friction says the force of kinetic friction is mu times the normal force. So I'm going to use that here. So I get T1 plus mu kinetic mg cosine theta, because mu kinetic times normal force that's the normal force, minus mg sine theta equals ma1. So that will be our equation 2. The last equation we have is the falling object, and the falling object, I've made it look like a cylinder, so I'll call it cylinder. Well, that's a simple equation. It's just sum of all the forces in the y direction equals capital M times the acceleration in the y direction. So that's going to be mg is acting in the positive y direction, T2 is acting in the negative y direction. A2. And that's our equation 3. These 3 equations have to be solved, equations 1, 2, and 3, along with the constraint equations that connect the two pulleys. So how best to do it? Well, let me write everything in terms of alpha. How about that? That might make it easier. So I'll write the first equation, RT2 minus little rt1 equals I sub p times alpha. The second equation I'll write next. So that's going to be T1 plus mu kinetic mg cosine theta minus mg sine theta equals ma1. And the last equation is mg. For a1 I'm going to write r times alpha. So let me just do that right now. Alpha times r. And the last equation I have is capital mg minus t2 is equal to m times a2, which is capital R times alpha. We'll have to solve that for alpha. But you notice all these tensions. However, if you multiply this equation by r, and this equation by capital R, and then add the equations, you'll see something interesting happening. That's RT2 and that's minus RT2. Well, they're going to cancel out. That's RT1 and that's minus RT1. That'll cancel out. So I just get this equation here, which is mgr, I'll put mg's first, plus mg little r mu k cosine theta minus sine theta is equal to I sub p plus mr squared plus mr squared times alpha. So I have this really beautiful looking expression for alpha. Alpha is equal to, it's I suppose beautiful for a physicist, it's mgr plus mgr mu k cosine theta minus sine theta divided by I sub p plus mr squared plus mr squared. So that's the alpha. Now once you have alpha, you can really solve the problem pretty straightforwardly. After finding alpha, you can find a1, which is r times alpha, so you know what a1 is. To find the stopping time, we use the kinematic equation, v final equals v initial plus acceleration times time. Now the final velocity is 0 and the initial velocity is just v. I told you it's just v. And this acceleration is negative because it's acting in the direction up, whereas velocity is acting in the direction down. So, or you can take this to be negative, I don't care. Plus a1, which is r alpha t, and that'll give you the t stopping. It tells you t stopping equals initial velocity v over r alpha, where alpha is given by this expression. And the stopping distance ls can be found In the same manner, the final speed squared equals initial speed squared plus 2 times the acceleration times the displacement, ls. And here you do have to be mindful of the fact that it's actually 2 times the acceleration times the displacement times the cosine of the angle between the two, which is cosine of 180 degrees here. So that's going to give me 0 equals v squared minus 2a1, which is r alpha, times ls. So I can get the stopping distance ls, which is v squared over 2r alpha, and alpha is again given by this expression. I won't write the full answers down, it's just a lot of writing, but that's basically how you do this problem.